Thank you. Thank you. All right. All right. Now it works. Now you can see both. Okay. All right. I'm going to do example 12, guys, which you can see now. Okay. This is example 12. You have theta 1, theta 2. Both these are unbiased estimators for theta, and you want to find a linear combination A1 theta 1 hat plus A2 theta 2 hat that is unbiased and also has the smallest variance of such a linear combination. Right, now to show that something is an unbiased estimator, you need to show what? You need to show that the bias, see, I've done this enough times, guys, you should know. To show that something is an unbiased estimator, you need to show that the bias is equal to 0, right? So that's what I'm going to do now. Remember, the bias is the expectation minus the parameter you're trying to estimate, okay? Which is this, right? Now we know that theta 1 hat and theta 2 hat are both unbiased estimators. So that means this is equal to A1 theta plus A2 theta minus theta. And this is equal to A1 plus A2 minus 1 times theta. And this is equal to 0 if and only if A1 plus A2 is equal to 1. All right, so what we have shown so far is that the linear combination, that is this one here, right? Can you see it now? The linear combination, this estimator, right, is unbiased, is an unbiased estimator for theta if and only if A1 plus A2 is equal to 1. All right? So let me write this down. So what we have shown is that is unbiased, is an unbiased estimator for theta if and only if A1 plus A2 is equal to 1. Right? All right, that's what we have shown. So let me put this in. All right, the next thing we need to do is to find the variance. Right? Remember, if an estimator is unbiased, then the MSC, the mean squared error, is equal to the variance. Right? So that's what I'm going to do. Let me put this over here, guys. Hopefully you can see this. Oh, yeah. Here we are. All right, so the next thing I'm going to do, guys, is to find the variance. Oh, it's here. I want to find the variance of the estimator of this estimator, right? Now we are told that theta 1 hat and theta 2 hat are independent estimators. If you read the question, guys, it says here that theta 1 hat and theta 2 hat are independent. Therefore, using independence, you can write this as A1 squared times the variance of theta 1 hat plus A2 squared times the variance of theta 2 hat. All right? You see how I get it, right? Using independence and when you, A1 and A2 are constant, so when you take them outside, you have to square them, right? Now, according to the conclusion of this, the first part, A1 plus A2 must be equal to 1. So that means we can replace A2 by 1 minus right, this is because A1 plus A2 is equal to 1. Yes, you're with me? Okay. Now, we are also told, you should read the question, guys, here. It says that the variance of theta 1 hat is equal to 3 times the variance of theta 2. Is equal to 3 times the variance of theta 2 hat. So using that, you can replace this guy by okay. Do you see what I've done? Yeah. I have replaced variance of theta 1 hat by 3 times the variance of theta 2 hat. Now this one you can write as this, right? Now, remember, the smaller the variance, the better the estimator, right? The smaller the MSE, the better the estimator. So we want to minimize this guy here. Now, how do we minimize this, guys? This goes back to your calculus. How do you minimize a function? This is the function we have, right? We want to minimize this function with respect to A, right? So what do? You should remember this from year 1, right? The first thing you do is take the derivative, so it becomes 6A minus 2 times 1 minus A. Then you set this to 0. It becomes 8A minus 2 equal to 0. So A is equal to a quarter. Now, this is not enough yet, because we need to make sure that this point, A equal to quarter, whether it corresponds to maximum or minimum. To do that, you need to do the second order derivative. The second order derivative of this is going to be 6 plus 2, which is 8, which is a positive number. Okay? So since the second order derivative is positive, what this implies, guys, is that A okay. So since the second order derivative is positive, we can say that A equal to quarter is a point of minimum of the function g, right? So in other words, what I am saying is that this guy here, you can see, if you can still see it, this guy is minimized if A1 is equal to a quarter. Okay, so let me put this over here. So the final conclusion is as follows. The yeah. So to answer the question, sorry, to answer the question, that an unbiased estimator of theta that has the smallest variance must be equal to this. So A1 is a quarter, so A2 must be 1 minus a quarter. So it's equal to this. All right, guys. So this is example 12, which you came late, guys, and wondering what I'm doing. This is what I've done is example 12 from the example booklet. All right. Other questions, guys? Sorry, you all right, sir? Did you copy this down? All right. Any other? So I'm just doing examples from this. Unless you have a particular question you want me to do, you can shout at me and I will do it. Yeah. Yes.
I wondered if you've got a question with an indicator function and so an MLE one, and you need the max to be below a positive value, the min to be above a negative value. I'm struggling with drawing the graph and working out.
All right. Let me see if I have one here. Do you have a particular question or no?
No.
Oh. You mean, like, for example, this one here, this is example 31 from the booklet. Are you okay with this one? Or
Yeah.
this?
I'm okay with that one. It's when it has to satisfy
Two conditions.
things at the same time, basically.
Oh.
So it could be all right with one, and then you could find the maximum, but then it could still be failing on another.
Didn't I do one like that in the uniform distribution? Remember the uniform distribution on the interval A to B? I think I did this before, but I don't know whether this is what you mean. Like, I mean, I think I did this question in the lectures, but are you able to follow this one? Or were you able to follow this one? Or no?
I think so. No, I can come and answer in
I can't think of other examples I can't right now. Unless you have a particular question, then I can go through it. Because this one involves two indicator function with two things in it.
Okay. I'll check that one again.
Okay, sorry. All right, any other questions, guys? Like any other particular question you want me to do? I'm happy to do it.
Did you do question 11 on the
11. You mean this one? Oh. Love. All right. Now, so you have a sample from, okay, consider an estimator that theta hat is equal to x bar. Find the bias and MSC. All right, to find the bias of x bar, you have the expectation of x bar minus theta, which is the expectation of okay. Now, to find the expectation of xr, you need to integrate this guy here, right? So basically, integrate x times the PDF, which is 2x by theta squared, dx from 0 to theta, minus theta outside, right? Now, you should do the integration. You get, you can pull out the constant. X cubed by 3, the limits from 0 to theta minus theta. Right? Taking the limits, we get 1 over n uh, 2 theta by 3 minus theta. Right, correct me if I'm wrong. So this will become 2 theta by 3 minus theta, so which is minus theta by 3, right? So what it says that is clearly, it implies that x bar is biased, right? It's biased because the bias is different from 0, 1. Yes. Now, you're also asked to find the MSC of it. So let me put this over here, guys. To find the MSC, you need to, you probably remember this formula that the MSC of an estimator, of any estimator, is equal to the variance plus the square of the bias. Yeah, I proved this quite a while ago. I proved this result, right? Now we know that the bias is equal to minus theta by 3. So this means that the variance of theta hat plus the square of this, which is theta squared by 9. So to find the MSE, all you need is to find the variance, right? So let's put a cross here. Yeah. So we need to find the variance, which is the variance of x bar, which is the variance of this. Yeah, taking the variance inside, you get 1 over n squared times the sum of the variance of xi. Yeah. Now we know that this is kind of stuff you probably know. I mean, the variance can be written as this expectation of xi squared minus the square of the expectation. Yeah. Now, if you look at what we have done over here, guys, you will see that we have already worked out the expectation of xi as being equal to 2 theta by 3. Okay? So we know this guy, right? So this becomes sorry, 2. So it's the square of this, which is 4 theta squared by 9. Yeah. So all it remains to be done is to find the expectation of the square of xi squared. So that means, so it's basically x squared times the PDF, which is 2x by theta squared, integral from 0 to theta of dx minus 4 theta squared by 9. Yeah. Doing the integral, you will get the sum 2 over theta squared. The integral is yes. Right. Now, taking the limits and you will see that this becomes 2 theta squared divided by 4 minus 4 theta squared by 9. Okay. Now, if you do the math, well, I'm sure you will get 1 over n squared times the sum from theta squared divided by 18. So this is theta squared divided by 18, and correct me if I'm wrong, guys. Is that right? Yeah. Okay. So that's the variance of theta hat, and we already know the bias. So in conclusion, let me put a cross here. The MSC of theta hat will be equal to theta squared plus 18n plus theta squared by 9. Right? So in this case, the estimator is biased and is inconsistent, because, as you can see, as n approaches infinity, this does not approach 0. All right? Therefore, the estimator is not consistent and is also not unbiased. Right? But the second part, I hope you can do the second part by yourself. Is that a problem? I mean, the second part of question 11. Yeah. Can you do that by yourself, or it just?
Not sure.
I'll give you a hint if you want. So the second part is asking you to modify the estimator so that the estimator is unbiased and consistent. So what you need to do, guys, is to realize that, you see, we have 2/3 here, right? So the new estimator, if you call it, say, psi, for example, you can define it to be 3/2 times x bar, right? You should call this. Now, in this case, I mean, you can be sure that the bias will be equal to 0. Can you see why? Yeah, because remember the bias of okay, and we showed over here, guys. We showed over here that the expectation of x bar is equal to 2 theta by 3. So this is 0, right? So this is how you do the second part of question 11. All right? Any other questions, guys? I'm sure you have plenty here. Yes. You guess? Yes, no? Huh? Okay, if you don't have one, I will do one, okay? Let's look at question number 45. 45, example 45 on page 6 of the booklet, all right? Example. Right, here you have 2 independent random samples. The first sample is from normal with these parameters. The second sample is also from normal with these parameters. And we are assuming that both mu x and mu y are known. And the question is to find the MLE for sigma. Right, so the only parameter that is unknown is sigma, right? So the likelihood is a function of sigma only, yeah? So the first thing you must do is to write down the likelihood, right? Because we have 2 independent random samples, I think I said this to you before. When you have 2 independent samples, what you do is the following. You first write the likelihood, the likelihood for the first sample, which is this one, all right? Then multiply that with the likelihood for the second sample. Okay? All right? Exactly. I think I mentioned this before to you guys. Whenever you have more than one sample, the likelihood is written like a product of two products, right? So this product for the first sample, product for the second sample, and the product of the two, right? All right. All right. Now simplifying this, you get the following. You get All right, this is the simplified form. I mean, once again, I must tell you, like I said yesterday in the lectures, it is very important that you know how to simplify likelihoods. And I'm telling this again because quite a few people did not manage this step correctly in the in-class test last week. So it's something you must work on, okay? Now, the next step is to take the log of the likelihood, the log of this, all right? And the next step is to differentiate the log with respect to the parameter. We have only one parameter, so we differentiate with respect to sigma, right? So differentiating this with respect to sigma, you get this. All right, you get this. Okay? All right, now the next step is to set this to 0 and solve for sigma. So let me put this over here, guys. Set that to 0 and solve for sigma. You get sigma hat squared hat equal to 1 all right, this is the solution. Now, this is not enough. Now, to show that this is an MLA, you must show that the second derivative of the log likelihood is negative at sigma hat. Now, I know I did not reduce mark for not doing that in the in-class test, but in the final exam, in 3 weeks' time, I will be strict when I mark the exam papers, because I will be looking for this step, that is showing that the second derivative is negative, right, at the MLA, right? But you only need to do that when you have one parameter, not when you have more than one parameter. You don't need to do that, all right? Okay, all right. So let's look at the second. Let's look at the second order derivative, right, which is the derivative of this, guys. So it's going to be m plus n divided by sigma squared minus 3 divided by sigma 4 all right. This is the second order. This is the second order derivative. Now, how do we show that this is negative? Any ideas? we need to show that this is a negative number, right? So let me show you how to do that. Now, to do that, I'm going to pull out this factor, right? And if you pull out this factor, you have m plus n sigma squared minus 3 times yeah? Right. Now, in the next step, I'm going to replace sigma by sigma hat, because we only need to show that the second order derivative is negative at sigma hat, right? So if I replace yeah. All right. Now we know what sigma hat squared is, right? You should go up slightly. This is the formula for sigma hat squared, or sigma squared hat. Now you should sub that here. Yeah, you should sub the formula here. You will get this equal to minus. Do you see why I get this minus? I'll explain that in a minute. Minus 2, there will be a 2 here. Just give me a sec, I will explain. Do you see how this 2 comes, guys? Yes? No? Some of you look lost. How do I get this 2? Because, look, this is the estimator for sigma squared hat, right? Now what I've done is to sub this into this, right? So if you sub this into this, you get exactly the same as this without the 3, right? Okay? So it is 1 minus 3, which is minus 2, right? And this is a negative number, right? And hence is this clear or no? Some of you look lost, guys. No? Is it not clear how I got this 2? Because if you sub in place of sigma squared hat, if you sub the estimator for sigma squared hat, you will get this reduces to this, right? And this is clearly a negative number, right? All right, guys? Yeah. Yeah, so sometimes showing that the second order derivative is negative can be tricky. It's not tricky. I mean, this is it's not really difficult, but it can involve some work, right? Showing that the second order is negative can involve some work. Yeah. Yeah. All right, guys. Okay. So let me put this over here. Hopefully. See this better? Right. Any other questions, guys? I mean, I know I have lots of questions here, guys, which I can do. Let me see if I can do some of. Well, let's do this one. 80. 89. All right, let me do this one. This will be the last one I will do today. So bring more questions you have for next week, all right, or tomorrow. You can also come to the example classes tomorrow and ask me questions. So this is example. Example 89, guys, is this one. All right, you have right, we have a random sample from a, guys, listen please. We have a random sample from a normal distribution with mean mu and variance equal to 1, and we want to test whether mu equal to 0 versus mu equal to 1. And the question is to find the most powerful test. So the first thing you must write is the following. By NP llama, we reject H0 if the likelihood at 0 divided by likelihood at 1 is less than a constant C, right? I mean, I think I have done enough examples on NP, so you should know how to do it, guys. Right, now, the likelihood at 0 you see how I got this, guys? This is the likelihood at mu equal to 0. This is the likelihood at mu equal to 1, right? All right, now a lot of things cancel. These two guys cancel out. Yeah? So what you get is the following. You get, on the top, you get this guy. In the bottom, you get this guy, less than a constant C. Yes? Right. Now, let's combine the two E terms. So you get E half less than a constant C. Yes? Now, open the brackets. All right, you get, if you open these brackets, you get half xi squared minus 2xi plus 1. And then we have a minus xi squared here too, less than a constant C. Now you see this guy cancels out with this guy, right? So what you have is E of, this is I, the sum of xi plus n by 2 less than a constant. Yeah? You see how I got it from this to this, right? Because these two guys cancel. So if you take the sum inside, this is what you get, guys. Right, now, the next step I'm going to do is I'm going to take the logs both sides. So you should take the log, you get sum of xi n by 2 less than log of c. Yes? I'm going to take this to the right-hand side, so this becomes sum of xi less than log of c minus n by 2. Now, finally, I'm going to divide both sides by n and multiply it by minus, right? So this will become x bar, and the less than will become greater than because I'm multiplying by a negative number. And so this will be 1 over n minus log of c plus n over 2. All right? So the rejection rule by the Neyman-Pearson-Lamar is that x bar, the sample mean, must be greater than this guy here, which I'm going to call a k. I mean, you can call it any other name, but just for the sake of notation, let's call it k, right? So the story so far is that here we are. So the story so far is that by NP-Lamar, we reject H0 if the sample mean is greater than a constant k. Now the next question, guys, is what is k? How to determine the value for k? Now to do that, I'm gonna use the alpha value here, which is 0.05, right? So we are told that alpha is 5%, so which means that the probability of type 1 error is equal to 0.05. Now remember, type 1 error is, I've said this many times, is the probability of rejecting the null hypothesis given H0 is true. So this is the probability that you reject, which is x bar greater than k, given that mu is equal to 0. Now this is where we go back a long way. Now you should remember the stuff we did in week 1 of this course. You should know the answer to the following. What distribution will this have? Do you guys recall? This is the first stuff we did in week 1. Mm-hmm. It's in the lecture notes, guys. You don't remember? And with parameters, what? Normal distribution with what is the mean? 0, yeah. And the variance? No. Come on, guys. The variance is 1 divided by n. Don't you remember this, guys? I mean, we did this. I think I told you, if you have a random sample from a normal distribution, then the sample mean also has the normal distribution with parameters mu and sigma squared by n. In this case, mu is 0, sigma is 1. So you have a normal distribution with 0 mean and variance 1 divided by n. Yeah? Is that clear, guys, or not? Now, how do we get rid of this 1 over n? Now, because to get rid of the 1 over n, we need to subtract the mean, which is 0, and divide by this, right? So you need to do that both sides, guys. Do you see why I'm doing this, guys? This is the, I'm sure this is known as, this is the standardization you're all familiar with. So this will be n01 greater than root of n k. All right? So that means root of n times k is equal to z, all right? And therefore k is equal to 1 over root of n times z. This is the percentile. Remember, the way I define percentiles in this course is different from other courses you have taken. So I define the percentiles, like in this case 0.05 is the area to the right. So it's this is the point on the x-axis of the normal curve that is exceeded with probability 5% or 0.05. All right? So to answer the question, so we are done nearly. By NP llama, we reject H0 with alpha equal to 0.05 if x bar is greater than this. All right, so this is the conclusion. Is that clear or not? I've done already like 5 or 6 examples already in with NP llama. So I hope really, I mean, you have to do, I mean, anything to, you have to do many examples, and then like you should be like, you will feel confident when you go to the exam. Yeah. Does it make sense or not? Does this? Yeah. All right, guys, if you haven't collected your test paper, could you please come forward and collect your paper? And I will be doing more revision problems tomorrow, 11 to 12 and 4 to 5 in Alan Turing, right? So please come to those if you can. Thank you. Okay, thank you. Thank you. You put your name here. Oh, did you put your name? Okay, thank you. Thank you. Thank you. Hi.
You see from here,
Yeah.
if they find the MA of the sigma, right?
Yeah.
The answer is always a sigma square.
Yeah, it's the same. So you just have to take the square root. Just take the square root of it.
For the answer,
Yeah.
I write sigma square or sigma, or I need to take the root.
Yeah.
I
Yeah.
just
Keep it like that. It's also it's fine. Yeah, it's fine.
Thank you.
Thank you. You guys.
Cheers.
You got your test papers. Yeah. Okay, thank you, ma'am. Okay. All right, thank you.